CDR's on the line.
CDR, OTC, good morning, Don. Let's do it today.
Sounds like a good plan to me, Bill. I'm for that.
Houston, Atlantis, MS1, contact.
Atlantis MS1, Houston, good morning. You're loud and clear.
That's great, and you're loud and clear also.
Roger that.
Good morning, Houston. PLT, com check.
Atlantis PLT, Houston, good morning. You're loud and clear. How many?
Loud and clear, Frank.
Thought you'd be higher by now.
So did I. Good morning, NTD. CDR here.
Good morning, how are you, Don?
Oh, we're doing fine. Al looks pretty out the window today.
Let's hope we get off today.
We'll vote for that. Good morning, Houston, from the CDR.
Atlantis CDR, Houston, good morning. You're loud and clear.
And so are you, Frank. Sound real fine for 8:45 in the morning.
Roger, we're ready in here.
Sounds good to us.
The United States Space Shuttle, a cornerstone of America's space program. With this sophisticated system of aerospace technology, America has a reliable vehicle for the scientific, commercial, and defense communities. A vital link to the construction and servicing of Space Station Freedom. The Space Shuttle consists of three major elements. Two recoverable and reusable solid rocket boosters. A non-recoverable external tank containing propellant and oxidizer for the main rocket engines. And the orbiter, the ship in which people and equipment challenge the elements of space. The orbiter is built primarily of aluminum and consists of three main components: the fuselage, the wing, and the vertical tail. The fuselage is divided into three sections. The aft fuselage carries the three main and two orbital rocket engines, plus the vertical tail. The mid-fuselage is the primary load-carrying structure containing the payload bay and payload bay doors. The delta wings are attached to the mid-fuselage. The forward fuselage includes the pressurized three-deck crew module with navigational, electronic, flight, and payload handling controls, as well as environmental systems and viewing windows. The orbiter's aluminum skin is covered by replaceable tiles for thermal insulation during the heat of re-entry. The overall length of the orbiter is 122 feet. It stands 57 feet high, with a delta wing that spans 78 feet. Cargo is carried in the payload bay. This compartment, 60 feet long and 15 feet in diameter, carries up to 55,000 pounds. Upon ignition, the shuttle will require more than 7.5 million pounds of thrust. Fed by the external tank, each of its 3 main engines generates 375,000 pounds of thrust at liftoff, while the 2 solid rocket boosters produce more than 3 million pounds each. The 2 pods on either side of the aft fuselage hold the orbital maneuvering subsystem. The fuel tanks carry nearly 24,000 pounds of propellant and oxidizer. Each engine is capable of 6,000 pounds of thrust. Once assembly is complete, the entire shuttle stack, including the launch platform, is moved to the pad in the vertical position. It is carried on the same crawler transportation system which carried the Saturn V moon rockets to the launch pad. On the pad, the shuttle stands poised for its orbital voyage. At T-6 seconds, the orbiter's main engines ignite. With the shuttle still bolted to the launch pad, the astronauts experience a twang effect as the stack sways slightly. Seconds later, the solid rocket boosters explode into life. The bolts release, and the shuttle rises on a column of flame toward orbit. During launch, the crew will experience no more than 3 Gs. Later, with the shuttle moving at better than 2,700 miles per hour, the boosters are jettisoned for recovery at sea. At 8.5 minutes, the main engines cut off and the external tank is jettisoned. It will not be recovered. At this point, the orbiter is at an altitude of about 70 miles. Once the orbiter reaches its highest altitude, the orbital maneuvering system boosts the ship into a circular orbit. This system also provides thrust for major orbital adjustment maneuvers, rendezvous, and deorbit, the burn to leave orbit and re-enter the atmosphere. To change attitude or point the orbiter, the reaction control subsystem is used. These small steering jets are also used for translations and as backup to the orbital maneuvering system. They are located in the 2 tail pods and in the forward fuselage. On achieving orbit, two Freon loops cool the orbiter's radiators, located on inner door panels, to provide cooling for the orbiter systems. Without this system, the orbiter could only withstand 3 orbits. After cooling, the payload bay doors are opened. From the payload bay to the crew compartment, the shuttle was designed to achieve the most economical use of space. The crew compartment consists of 3 levels. The middeck contains the living area, 95% of the onboard storage. The airlock. And airlock hatch. And the waste management facilities. Sleeping accommodations and optional seating for up to 3 crew members are also found on the middeck. The middeck also contains a galley for the preparation of hot meals. A crawl space beneath the middeck contains environmental control equipment, including oxygen, water, and other subsystems. Above the middeck is the flight deck. Here, as many as 4 crew members may be seated during launch. The controls for piloting the orbiter in space or atmospheric flight are located on the forward flight deck. Control may be either manual or automatic. All navigational and electronic equipment is also found on the forward flight deck. A second flight control panel is located at the aft flight deck. Controls for the payload station, as well as the remote maneuvering system, are found in the aft flight deck. Using the remote control manipulator arm, the crew is able to place the payload into orbit. The manipulator arm can also be used to bring an orbiting satellite on board. As many as 8 video cameras in the payload bay and on the arm assist the crew with payload operations. 4 aft windows also help the crew with payload observation and orbiter positioning. For medical and scientific research missions, the payload bay can be modified by integrating a laboratory module called Space Lab. Higher orbit or deep space probes can be put into a parking orbit with an inertial upper stage booster for on-orbit launches or deploys. Exiting through the airlock, crew members can venture outside the orbiter to perform a variety of tasks. Specially designed spacesuits are worn for protection. Individual manned maneuvering units are also available. Yet even as the human crew goes about its task, another system is at work. The same network of 5 onboard computers that precisely control the launch and orbit entry sequence also continuously monitor and control the onboard systems. For some functions, such as rendezvous, the system is designed to perform interactively with crew inputs. This system will also control the orbiter through re-entry until just before touchdown. With the mission accomplished, and with deorbit preparations made to leave orbit and re-enter the atmosphere, the payload bay doors are closed. In emergencies, a backup manual closing mechanism can be used. The orbital maneuvering subsystem is used for the deorbit burn to head the orbiter back to Earth. Here, as well as during launch, the function of the thermal tiles is crucial, since re-entry temperatures can reach a searing 3,000 degrees Fahrenheit. The normal mission duration is 7 days, but this has been extended to 13 days in the past on a modified orbiter. Plans to modify the entire fleet of orbiters for longer missions are underway. After touchdown, a drag chute is deployed from the back of the orbiter. The chute was designed to improve braking and steering control during landings. Once on the ground, the mission is over, but the career of the orbiter goes on. At the Space Shuttle launch facility, NASA's Kennedy Space Center in Florida, the next orbiter is readied for its flight. Each orbiter is designed to fly at least 100 missions, opening the door to increased space exploration. The United States Space Shuttle, a dependable and versatile means of space transportation, providing untold benefits to the people of Earth for decades to come.